Okay guys, today we are going to continue our work on vectors, and what we're going to look at today is the magnitude direction form of vectors. And so far what we've really been looking at is component form, where I could have a vector like 3, 2. And somebody tell me like what the vector 3, 2, like tell me how you would get there.
You would use,
just if you're going to draw it.
to be,
okay, 0, 0.
you go to the right 3.
1, 2, 3,
and
right?
up 2.
1, 2, okay? So, you know, that's exactly right. If we were a little bit more formal, we would say this is the I direction, this is the J direction. That would be 3I plus 2J, okay? And so we go 1, 2, 3 in the I direction, 1, 2 up in the J direction. Okay, so that is the component form. That really, really makes a lot of sense. All right, but what I want you to see is, besides doing it like coming over 3 and up 2 and kind of building a triangle, there would be another way that we could do it, where we could describe this same vector, let's say, this same vector with two numbers. One is a magnitude, like how long is it, and then the other thing would be what? The angle, okay? The angle. So I'm this long and I'm pointed in this direction based on an angle. And so you see you could work all the problems in component form, or you could work everything in the magnitude direction form. And what we call this magnitude direction is polar form of vectors. Okay, so that would be a good title for this, the polar form of vectors. And actually this is kind of a nice way to do it. So like the way I would write this vector, so this would be kind of like, a number and a number, right? So you like have this far this way and then this far this way, a number and a number in component. This is the way you write it in polar form. You have a magnitude A and an angle theta, all right? And this is how you would write a vector in polar form. You have a magnitude A and then you have an angle. Does that make sense? Let's see if I can get a better pen going here. So let's think how we go back and forth between one and another. So let's see if you can figure this out. I'm going to start in polar form. So I have some what on this vector? Tell me what two things I have.
Magnitude.
A magnitude A and an angle theta. Now this is polar. And I want to go polar to component form. So what we are doing here is how to go from polar to component. So if I want to be in component form, what do I need?
You need 2 numbers.
I need 2 numbers. So can we kind of draw it like this so we're at least starting right? Okay, what number goes here? Like if you think of this picture, what number would go here? Just kind of talk out loud. I want that first number.
The I?
Yeah, it's in the I direction, so it would be kind of like you would make a triangle, right?
Mm-hmm.
So I would sort of have the I part and I would have the J part. Well, if you look at this, do I know the I part just right off the bat? No, but can I figure it? What would I be? What would the I part be?
4.
What?
4.
Well, no, I mean just in general, like the
Would
equation.
It be
You have an A and a theta, so how would I?
the A.
It would be the A?
It'd be side angle side.
Oh.
So
It's a lot simpler than that. This is a what kind of triangle?
Oh, a right triangle.
Oh, right.
So what am I looking for?
You're looking for I, which would be either A or B, so you can use.
Could you use SOHCAHTOA?
Yeah, it's simple, Ben. It's simple. It's SOHCAHTOA. So what would be the simplest thing to do? Cosine is equal to adjacent over hypotenuse. What do I have here?
You have the hypotenuse.
I have the hypotenuse, okay? And what am I looking for? I'm looking for the adjacent. So I would say the adjacent is equal to cosine of what?
Cosine of the hypotenuse. No, cosine of theta times the hypotenuse.
Cosine of theta times the hypotenuse, which is A. So this is simply A cosine theta. This leg here would be A cosine theta. And then what would this length be?
Sine.
A sine theta.
A sine theta. Okay, so this is A sine theta. All right. So do you see how is it hard or easy to go from polar to component form?
Easy.
It's very, very easy. Okay, just the I term is A cosine theta, and the first term is A cosine theta. The second term is A sine theta. And then if you wanted to write it in unit vector form, you could say V is equal to A cosine theta times what?
Wait.
A cosine theta
Theta.
times hypotenuse.
A vector needs what two things?
The direction and the magnitude.
This is the what?
Oh,
Magnitude.
that is the magnitude.
So what do I need?
A direction.
And what's the direction associated with that?
Theta.
Okay. Okay, I'm just going to go ahead and teach it, and then you guys can just try to follow along, okay? This is I plus A sine theta J. Okay, so I can go from polar to component to unit vector form. Okay, how do we go the other way? Let's see how we go the other way. The other way is we want to go from component to polar. Okay, if we want to go from component to polar, what I'm going to have is I'm going to have some A that I go in the I direction, and then I'm going to have some B I go in the J direction. So I'm going to say vector V is equal to A times I, A in the I direction, plus B, and this should have been J, B in the J direction. AI plus BJ. In order to go to polar form, what I need is I need an A. So I'm going from that to I need an A, and I need an angle. Okay, I need an A and I need an angle. Well, how do I get A? A is the magnitude. So the magnitude is going to be, A is going to be the magnitude of V, which is going to be equal to the square root of A squared plus B squared. Okay, so what I have here is I start with A and B, and then my A is an angle of theta. I want to go there. A is going to be equal to the magnitude of V, which is the square root of that A squared plus B squared. Okay, now what I need is I need an angle. So the angle is this angle here, all right? And what would that angle be? Well, I know that SOHCAHTOA tangent of the angle is equal to opposite over adjacent. So tan of the angle is equal to the opposite, which is B, over the adjacent, which is A. So tangent theta is opposite over adjacent, which is B over A. So theta is equal to tan inverse of B over A. Theta is equal to tan inverse of B over A. So here I need angle, I need a magnitude at a certain angle, and here the theta is going to be tan inverse of B over A. So what I've shown you here is I've shown you that you can go from polar to component, or you can go component to polar, and you just do it with, all you do is you just...
Question. Okay, so you would use you did the whole like A equals the magnitude of the vector.
Mm-hmm.
So you do that, and then you find what theta is, and then you just use that to write A is greater than theta?
No, this is A at an angle of theta.
Oh, okay.
Yeah, okay, so it's like that. It's A at an angle of theta. So it's this long in this direction. Okay, so you can go component to polar, polar to component, and really it's just SOHCAHTOA, that's all it is. Okay, so what I want is the component form of a vector for an airplane descending. So if I'm going to draw a picture, it's descending at 20 degrees below the horizontal. So that's the direction, right? Like you could think this is 20 degrees. Component form of a vector of an airplane descending at 20 degrees below horizontal. Does that picture make sense? Okay. And it's going at 150 miles per hour. So I have a magnitude, 150 miles an hour, and I have a direction. Okay. Then what I want to know is I want to know, you know, how fast it's going horizontally and how fast it's going down. So this is really polar form, 150 degrees at 150 miles per hour at 20 degrees, and I want to go from that to I want to go to component. And so really what my vector is 150 at an angle of minus 20. Okay, that is my vector in polar form. So now to get this in component form, I got to figure out how far across this is and how far down this is. And then that would be kind of like the first and the second number. Well, what I can see really clearly is that I can just put in those equations earlier that I had, and this is a 150 cosine of minus 20, and then this is 150 sine of minus 20. Okay? 150 cosine of minus 20, 150 sine of minus 20. That's just solving the triangle. And then what you get is you get 140.96, and you get minus 51.3. Okay? So this speed in this direction is 140.96. This speed in this direction is minus 51.3. Okay? Does that make sense? So that's pretty simple what we've done. Now the problem with polar is it's very hard to add two vectors, right? if I have component form A, B, and C, D, and I want to add those two, it's A plus C and B plus D, right? So adding in component form is very easy. But how do we add in polar form? Okay, you have to convert to component form. All right. So we're gonna do it this way. So let's say that we're gonna add two vectors. So an airplane is traveling 500 miles per hour at 120 degrees. There is a wind of 70 miles per hour at 45 degrees. So what do I have? I've got one vector, which is the plane, 500 at an angle of 120, and then I have 70 miles per hour at an angle of 45 is the wind. So if I drew that, this would be 90, 120 would be like here, so that's like 120, all right? And then this, the magnitude is 500, and then I have 70, and then this angle is 45. So I have two vectors. How do I add the two vectors? I got to break it into the components. So I'm going to call it, like, we'll call this U, and we'll call this V. So U is going to be equal to, how do I break this into the two parts?
It would be 70 times cosine of 45.
Uh-huh.
And then that would be 70 times sine of 45.
70 times sine of 45. Okay, V is equal to 500 cosine of 45, and then 500 sine of 45.
Would it be cosine of
120.
120?
Thank you. 120. 120. Okay, so now I've got an I part and an I part, and I got a J part and a J part. So what is the sum? The resulting vector would be this plus this and that plus that. So it would be equal to 500 cosine 120 plus 75 cosine of 45. Okay? And that's the I part, plus 500 sine of 120 plus 75 sine of 45. Okay, so it's this, and then this is the J direction. Okay, when you put that in,
Hold on, where did R come from?
this is just what you result. This is the answer.
Oh.
Okay, so this is the result of adding the two. All right, so when we add all that up, the resulting vector is equal to minus 200.5 in the I direction plus 482.5 in the J direction. Okay, so that is the resulting vector. Now, the problem, though, is the problem was given to you in what form? Polar. Now, I've got an answer, but I got to give it back to you the way you gave it to me. So now I have to convert this to what?
Polar.
Polar. So what is the magnitude of R? The magnitude of R would be the square root of 200.5 squared plus 482.5 squared, and that is equal to 522.5 miles per hour. Okay, now I need to find the angle.
Mr. McCord, I'm sorry. Oh,
On that
Uh-huh.
equation that you just erased, you wrote down 75 instead of 70. Is it 75?
I'm sorry, it's 120 and 45, and the magnitude is 70. So if I wrote it down wrong, the magnitude is 70.
Yes.
Okay, thank you. All right, so 522.5 miles per hour. Now I have to find the angle. Well, the angle is going to be equal to tan inverse of, let's see, the opposite over adjacent, 482.5 over, and I got a negative sign in there, be sure to put the negative, minus 200.5. And then what I get the angle to be is 112.56 degrees. So if I have 500 at 120 and 70 at 45, I break the 500 into two vectors, this one and this one. Then I break the 70 at 45 into two vectors, this one and this one. Okay, I add them together and then I get this, but now I got to convert that back to something else, and then what I get is 522 at 112. So like the answer is something like this. And that is the magnitude of 522 at an angle of 112.5. Okay, does that make sense? So what do? If you're going to add in polar, you got to get the I and j of the first vector, the I and j of the second vector. You've got to add them together, and then you've got to convert it back to polar. Any questions? Okay, I think this is it for Chapter 6, Section 3, and I think we have the homework up here already. Does that make sense?
Yes.
All right.